Welcome to the AP Calculus BC video for skill number 215 and 216. I can extend my algebraic laws of limits to find infinite limits if they exist, and I can use infinite limits to explain asymptotic behavior. So skill 215 is more about taking limits of functions, and those answers to the limits are approaching positive or negative infinity. And then skill 216 is you are taking the limit as x approaches positive or negative infinity. And that's the difference between the two. Generally, both of them result in discovery of asymptotes. This one is going to give us vertical asymptotes, and this one is going to give us horizontal asymptotes. Sometimes, not always. Alright, we'll start our notes on page 215A for skill 215. And we've already worked with limits of rational expressions, and this is kind of an extension of it. We want to take the limit as x approaches 3 of this function. And if we do simple substitution, we arrive at an answer of 6 over 0. And that does not exist, so we can't do straight up simple substitution. So then we use the method that we should already know, which is factoring. And if we factor, what we find out is that the x plus 3 cancels out of the top and bottom, and now I'm taking the limit as x approaches 3 of 1 over x minus 3. And again, simple substitution does not yield an answer. So we should take the left side and the right side limits. So I take the left side, and I can think of that as plugging in something like 2.999999 into there, and I wind up arriving at what is roughly to be a very small negative number, so the limit approaches negative infinity. When I do the same thing for the right side, I'm substituting in something like 3.000001, and I wind up getting 1 over a very small positive number, so the limit approaches positive infinity. Since the left and right side limits are not equal, the limit does not exist. Since both limits approach positive or negative infinity, we have a vertical asymptote at x equals 3. So x equals 3 is right there. As we approach it from the left side, we go to negative infinity. As we approach it from the right side, we go to positive infinity. Here's a second example. The limit as x approaches 0 of 2x minus 9 over x squared. And if we plug in 0 by simple substitution, we get negative 9 over 0, which isn't possible. So we need to switch over to taking the left side limit and the right side limit. So if we take a number that is just left of 0, what we're going to wind up having is approximately negative 9 on top, and then a very positive small number. So we're going negative divided by positive, more or less positive 0, so we get an answer for the limit, the left-hand limit of negative infinity. If we do the right-hand limit, we're going to get the same thing where we have negative 9 in the top, or close to negative 9, and a very small positive number as well on bottom. And a negative divided by a positive yields a negative answer again. So since these two match, the limit as x approaches 0 goes to negative infinity. Okay, moving on to skill 216, I can use infinite limits to explain asymptotic behavior. So in this case, we're looking at the limit as x approaches infinity when I say infinite limits. And example 1 asks us to find as x approaches infinity for 2x squared plus 5 over 4x squared plus 7x minus 5. And we can't really do any factoring per se, and if we were to do direct substitution, we'd wind up getting some strange thing like infinity plus 5 divided by infinity plus infinity minus 5, and that yields some sort of infinity over infinity. We don't know how big those infinities are, and that's an interesting mathematical discussion, but this doesn't work. So we need to arrive at some other method to calculate this limit as x approaches infinity. A very common approach for rational functions is to divide each term, or the numerator and the denominator, by the highest powered x. And since our highest powered x is x squared, we could take the whole function 2x squared plus 5 divided by x squared, and then take the denominator of 4x squared plus 7x minus 5 and divide that all by x squared. And that's what I've done here. I've broken it onto each of the little smaller fractions and simplified 2x squared over x squared becomes 2, and then 5x squared, or 5 over x squared, becomes 5 over x squared, and I continue to do the same process for all of the things in the denominator. Now, when I want to calculate the limit, I remember that the limit as x approaches 0 of a constant divided by x raised to a power is 0. So if I take the limit of each of these, what I'm getting is the limit as x approaches infinity of 2 is 2 plus 0 all over 4 plus 0 minus 0, giving me a final value of 2/4, which is 1/2. Which means we have a horizontal asymptote at 1/2, at least on the right half of the graph. So it could be doing that, or maybe it's coming down. We don't know. We'd have to explore the function a little bit more to determine what side it's on.
I got it like a wrecking ball.
Continuing on with example 2, what we have is a similar scenario where we have a polynomial divided by a polynomial. And so what I can do is I can divide everything by the highest power, which is x to the third. So we divide the numerator by x to the third and the denominator by x to the third. And that, when we cancel out our terms, gives us this value. And then we're going to evaluate as x approaches negative infinity. And the same scenario happens where the limit for 3 is 3, for this is 0, this is 0, and this is 0. So we're getting 3 plus 0 minus 0 all over 1 minus 0. So our limit as x approaches infinity, as x approaches negative infinity, is positive 3. So we have another scenario where our horizontal asymptote is at y equals 3. So as we go further out to the left, we eventually approach negative 3. Further analysis needs to be done to decide from which side. It should be noted that not all functions have the same horizontal asymptote. Be sure to check both limits if you're being asked to find the horizontal asymptotes. For example, the function tangent arctan, or tangent inverse, has 2 horizontal asymptotes, and if you remember the graph of arctan, it looks something to the effect of this, with horizontal tangents at pi over 2 and negative pi over 2. Horizontal asymptotes at those values. So in the final example, example 3, we're asked to find horizontal and vertical asymptotes of the given function, and I quickly found the vertical asymptote by saying the denominator cannot be 0, and that means x cannot be negative 2. Now whether that's a whole or a vertical asymptote requires me checking to see if there's a term of 2x plus 4 in the numerator, which there is not, so we're fine. 2x plus 4 is a vertical asymptote. Now we need to find the horizontal asymptotes, and this is a little bit more tricky. Let's take a look at the next page. When a question is asking to find the horizontal asymptotes in calculus, what you can think of that is that it's saying calculate the limit as x goes to infinity, and then also calculate the limit as x goes to negative infinity. So we're doing that for this equation first, for the horizontal asymptote on the right side, so as x goes to infinity. We don't quite have a rational expression. We do have an algebraic expression, and the pattern that we've used is we've divided by the highest power. So in this function, the highest power is x, because if we take the square root of the x squared, we get x. So we're going to divide everything by x. So in the denominator, 2x divided by x plus 4 divided by x. And the numerator, it's x on the outside of the radical, so on the inside of the radical it's going to be x squared. So 5x squared divided by x squared minus 1 divided by x squared. And when we take the limit of the inside, we're going to wind up having the square root of 5 minus 0. And if we take the limit of the denominator, we have 2, which gives us the final limit calculation of root 5 over 2. So that gives us the right-hand horizontal asymptote, but we now need to also calculate the left-hand horizontal asymptote. So we're going to calculate the limit as x goes to negative infinity of the function. And we recall that what we did is we divided everything by x, or you could think of that as multiplying by 1 over x. So you divide the numerator by x and you divide the denominator by x. But because we're approaching negative infinity, you have to think of the division as being negated. This is a slightly more difficult thing to understand. If you want to see an example and read from the textbook, take a look at page 134 of our Stewart textbook. Very briefly, you can think of the fact that when you take the square root of a number, it's going to, by definition, give you the positive answer only. But we're talking about the limit as x goes to negative infinity, so in theory we could have a negative answer. So we negate it as we're taking the square root, and then we can feed that into the problem much in the same way that we did last time, where we had, oops, let's grab a pen, 5x squared over x squared minus 1 over x squared, and that's all square rooted. And then the bottom simplifies the same. As we continue to carry out the limit, we find that the limit is virtually identical to the right-hand side. The only difference is that we have a negative out here now. So we can use one of our limit laws to move the negative to the very front, and we get the limit as x approaches negative infinity of this function to be negative root 5 over 2. Now it just so happened that our two horizontal asymptotes were positive and negative of the same value. This is not always the case, so don't just make that quick assumption. We'll try to show examples in class of other scenarios like this, because this is a more challenging problem. Thanks for watching the video for skill number 215 and skill number 216.